Welcome back to Elementary Algebra. I am your instructor, Amy Fuchsteiner, and we are going to interrupt this solid algebra section to introduce you to some scientific notation, which you may or may not remember from science class. It is in this chapter because we are going to be using exponents, and so we needed our exponential rules as introduced in 5.1 and 5.2, the last two sections, in order to be able to manipulate our scientific numbers. So, what is scientific notation? Scientific notation is a way of writing very large and very small numbers. Numbers that are too big to fit into your calculator in terms of how many digits they have. Not necessarily in terms of how big the actual numbers are, but in terms of I need 12 spaces and my calculator only has 8. So we have scientific notation. All right. Scientific notation has two parts. The first part is known as the coefficient. The coefficient in scientific notation is, let's say A. We're going to call it the coefficient A. And it is bigger than or equal to 1. So it can be a 1, but it has to be less than 10. This is how we describe that coefficient. It needs to be between 1 and 10. It can be 1. It cannot be 10. Sometimes you hear people say that you need one digit to the left-hand side of the decimal point. You can have all kinds of digits to the right, all kinds of digits after the decimal point, but you can only have one digit prior to the decimal point. And that is generally scientific notation. It is then multiplied by some power of 10. So 10 to some blank power. This power is an integer, meaning it's a positive or negative number. It can be positive and it can be negative, okay? So it is always in the form of A times 10 to some power n. What do we know about A? It is between 1 and 10. And what do we know about the n? That guy's got to be an integer. All right. Are the numbers I'm listing here in scientific notation? If they are, great. If not, what happened? What's off? Right? So for number 1, we have 2.9 times 10 to the negative second. Is this in scientific notation? It certainly is set up like it. Is your coefficient A between 1 and 10? Why, yes, it is. Times 10, that's correct, times 10 to the nth power, where n is an integer. Is your n value a positive or negative number? Negative 2. Yes. Yes, this is in scientific notation. Yep. Good. All good. Check. What about problem number 2? Problem number 2 is 13.75 times 10 to the third. Looking at your coefficient, that's the number in front, is that between 1 and 10? It's 13.75. That is not between 1 and 10. That is bigger than 10. So is this in scientific notation? No, it is not. Why? 13.75 is bigger than 10. It's greater than, that looks like my 7. It is greater than 10. So that means it is not in proper scientific notation. The times 10 to the third is good. It's just that this coefficient part right here, this part, that's what ruined it for us. What about number 3? 0.05 actually, times 10 to the negative 7th. Again, as we look at this coefficient, is that between 1 and 10? 0.05 is smaller than 1. It's like a nickel out of a dollar, right? It's smaller than 1. So this part does not work. So this is again a no. Why not? 0.05 is actually smaller than 1. And we can't have that. It's got to be between 1 and 10. What about a 2.25 times 5 to the negative second? A 2.25 is fine. That's a coefficient. It's between 1 and 10. We're good. Times 5. Oh, right there. I can't have a 5. This is a no because we're not doing a base of 10. It's a base of 5 in this example, not a base of 10. Base 10 is needed. Okay? What about problem number 5? I have 1 times 10 to the 0. In order to be proper scientific notation, the coefficient of 1 has to be at least 1, but less than 10. So as 1, that is fine. It works. It's all good. Then I need times, got it. 10, got it. To the nth power, got it. I don't like that n is 0, but this is fine. It is in scientific notation. It is 1 times 10 to the nth power. It works. It's not a perfect one, but it works. What about problem number 6? Problem number 6 says 10 times 10 to the 5th. Well, it was okay when it was 1, but is it okay when it's 10? No, it has to be smaller than 10. It's not including 10. So less than 10 means 9.99999 would be okay, but 10 is not. So this is not good. And this time it's because that coefficient, IENT, I can't spell tonight, that coefficient is 10, and it's got to be less than 10, right? Okay. So what do we do to write numbers in scientific notation? Well, there is going to be a pattern here. You will likely figure it out. And that is that very large numbers are 10 to the n where n is positive. So when the exponent on the power of 10 is a positive number, then we're talking about very large numbers. And if a number is very small, then we still have a times 10 to the n, but n is positive. Or n is negative. Okay. I generally start out by doing any number as times 10 to the 0, because 10 to the 0, anything to the 0 power, is 1. And this helps me to adjust. So how does this work? Well, here I have 2,000, or what is that? Hundreds, thousands, millions, billions. I have 2,340,000,000,000. I'm going to write that as times 10 to the 0. Okay? Because times 10 to the 0 is just 1. That's all that is 1. Now, the idea here is you figure out where your decimal point would go. The decimal point would and should go right here, after the last 0 and or digit. If there's not one there, it goes at the end, right? So now what I want to do is figure out, for scientific notation, I need the number to be between 1 and 10. So I need to move this decimal point all the way over. Not to the 4, because that gives me 234. Not to the 3, because that gives me 23.4. But between the 2 and the 3. So I need to move this decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places. In moving the decimal point 12 places to the, what direction is that? What direction is that, Amy? That's left. 12 places to the left. My exponent is going to go up 12. So for every decimal place I move to the left, my decimal or my exponent goes up 1. Basically, it's a balancing act. By moving the decimal place to the left, I'm dividing by 10. So when I add 1 here, I'm multiplying by 10. So for every place that I divide by 10, I need to multiply by 10. That undoes it. That keeps me balanced and equal, right? That means that in scientific notation, this number is 2.34 times 10 to the 12th. Perfect. Let's look at problem number 8. Problem number 8, I would rewrite as 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would go 0.02345678245 times 10 to the 0. I need to move my decimal point. It's already there. I need to move my decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9. So I got to go 1, 2, 3, 4, 5, 6, 7, 8, 9 places to the right. And when I go 9 places to the right, that's going to subtract 9 places from my exponent. So this one will be 2.45 times 10 to the negative 9th. Beautiful. 14 times 10 to the 0. My decimal point is here. I can't have 14. It's bigger than 10. I've got to move it 1 place. That's going to add 1. So this will be 1.4 times 10 to the 1st. Honest to God, we would probably just call it 14. Doesn't make any sense to call it 1.4 times 10 to the 1st. But sometimes that's what you get in the middle of a calculation, and so you just run with it. 0.088. I would write it as 0.088 times 10 to the 0 power, because that's just a 1. And my decimal point needs to go between the 2 8s. So that's 2 places to the left, which subtracts 2 from my exponent, or 8.8 times 10 to the negative 2nd. Right? I like this method, this idea of moving the decimal point and whether your exponent goes up or down, for a couple of reasons. One of the things I do is, we saw with the last one, my little rules for exponents, right? So one of the other things that I do is I use this way of remembering called heads together, butts together. All my little tricks, right? So heads together, butts together is the description of the arrows on these. So when your arrow for the decimal point goes out, the arrow for the exponent goes up. See how the butts of the arrows are together? And when the arrow for the decimal point comes in, the arrow for the exponent comes down, heads together. So the heads of the arrows are together, or the butts of the arrows are together. And this is one of the things that I would write on my papers when I did scientific notation to help me remember how things went, heads together, butts together. And it helped me keep things straight. And I tell you in hopes that it also helps you. Okay. Ooh, I think I might have got it. All right, we've got some conversion problems here from scientific notation to standard notation. We can use that same sort of method that if the exponent has to go up, the decimal place moves to the left. And if the exponent has to go down, the decimal place moves to the right. What does that mean in actual practice? Here I have 4.08 times 10 to the negative 2nd. If I want to put this in standard notation, I've got to make this times 10 to the 0, because 10 to the 0 is 1. So I need my exponents to go up 2. And if my exponents are going up 2, then my decimal point needs to go out 2. That's the idea of butts together, right? This guy. So this would be 0.0408 would be times 10 to the 0, or 0.0408. That would be my standard notation. Okay. If I'm doing number 12, which is 2.6 times 10 to the 12th, In order to get this into standard notation, I will need to subtract 12 to get it to 10 to the 0, which is 1. And if that's the case, if this is coming down 12, then my decimal point needs to move to the right the same number or 12 places. So that's going to be 2. 6 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whew. And then that would be times 10 to the 0. 10 to the 0 is just a 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That tells me where my commas go. 2, 6, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. Whew, I feel like Siri. There we go. What number is that? Hundreds, thousands, millions, billions, trillions. This would be 2,600,000,000,000. All right. 1.45 times 10 to the negative 5th. To get this to 10 to the 0, I need to go up 5, which means my decimal point will need to go to the left 5. So 5 in that direction. So I'm going to have 0.1234145 times 10 to the 0, which would just be 0.0000145. There she is in standard. 8.33 times 10 to the 5th. This one would need to come down 5, which means that decimal point would need to go right 5. So that would be 8, 1, 2, 3, 4, 5 times 10 to the 0. 3 places for a comma. 833, comma, 0, 0, 0. How would I say this number in standard notation? These are the ones place and these are the hundreds. So that's, or thousands, sorry. These are the hundreds, these are the thousands. So 833,000. That's what that number would be. Oh, and I didn't do the decimals. So just for practice, how would I say 0.0408 other than saying 0.0408? I look not at the zeros, but I look at this and I see 408. So this would be 408 tenths, hundreds, thousands, 10,000s. So this would be 408 10,000s would be the actual number here. This one would be 145 because there's just 3 digits at the end. So I would say it like 145. But then I need to know what place this is. That's tenths, hundred, thousandths, 10,000s, 100,000s, millionths, 10 millionths. So this is 145 10 millionths. That's a very small amount. Very tiny. Very, very tiny. All right. Couple of word problems. We're basically just going to try to get you to convert, and there might be a little bit of multiplication here. All right. So the speed of sound in air is approximately 3.3 times 10 to the 4th centimeters per second. Express this in kilometers per second. So what you need to recognize is that there are 100 centimeters in a meter and 1,000 meters in a kilometer. So if we have 3.3 times 10 to the 4th centimeters, right, per second, then we need to, that's centimeters in 1 second. Then we need to express this in kilometers. Well, we know that in 1 meter, there are 100 centimeters. And there are, let's see, 1,000 in 1 kilometer. There are 1,000 meters. Okay, so I need to take 3.3 times 10 to the 4th. And I need to divide that by, let's see, that's going to be 1, 2, 3, 4, 5. 3.3 times 10 to the 4th divided by 1 times 10 to the 5th. Why would I do that? Well, now I can separate it like bases, right? I have 10 to the 4th over 10 to the 5th, and I have 3.3 over 1. So this would be 3.3 times 10. Bases are the same, so I can subtract 10 to the negative 1. So this would be 3.3 times 10 to the negative 1, or basically a third of a kilometer, 0.33. Okay. All right. Oh, the fastest computer one. I don't know which syllable to stress because it's Japanese. The world's fastest supercomputer, Fugaku, is in Japan. It performs at a rate of 442.01 petaflops per second. Now, a peta or a petaflop is, it's the same as 4.42 or 442.01 times 10 to the 15th operations in 1 second. So what number is that? 442.01 times 10 to the 15th? Oof. Write this number in scientific notation. It's not in scientific notation. Do you see that? That 442.01 is bigger than 10, and I need it to be less than 10, which means I need to move this decimal point 2 places. And if I move that decimal point 2 places to the left, that's going to move that 15 up 2. So in scientific notation, this would be 4.4201 times 10 to the 17th. Nice. The fastest computer in the U.S. is called the Summit, and it's located in Oak Ridge National Laboratory in Tennessee. Who would have thought Tennessee? If Fugaku is 2.8 times the speed of Summit, find the speed of Summit. So Fugaku is faster by a factor of 2.8. So I'm going to take 4.4201 times 10 to the 17th, and I'm going to divide that by 2.8. In scientific notation, what we would do is actually just this division. So I'm going to take 4.4201, right? 4.4201, yep. And I'm going to divide that by 2.8. And I'm going to get 1.5786 times 10 to the 17th, because I have no base there, so I have nothing to subtract. So that's just going to stay times 10 to the 17th. Is this in proper scientific notation? Well, that coefficient is between 1 and 10, so that works. It's good. So 1.578 times 10 to the 17th would be the processing speed of Summit. Hoy, that's still very fast. Petaflops, gigaflops, megaflops. I'm not sure what a flop is, but a flop measures the speed of a calculation on a computer. That much I did glean from this. So, all right. So the practice in this is just a lot of moving scientific notation around some operations. Please don't hesitate to reach out to myself or to get help from the Math Center if you have questions on any of the scientific notation stuff. We'll see you in a heartbeat not a heartbeat. We'll see you in a few beats for 5.4. Thanks.